Okay, so now let's launch Fluent. So we are going to do the same setup as we did in 2D, which 100,000. We're going to do it as well. So inlet, outlet, and viscosity and everything, same method. So it will take longer because it's 3D. So choose any of these cases. I will do it just with one. So choose here Fluent, and we will choose this one, the same model, which was this nicer mesh. Okay. Oh, sorry, I need to put it in Fluent, put it here, okay. Update just to convert the mesh into Fluent, and then see here that you have all the meshes. Okay, so see that we have two Ansys meshes here, and then we're converting the one corresponding to this one. Okay, we have our mesh. Okay, check mark. You can do the same here, just drag and drop and convert that. We will just work with one. So now that you are here, just double click, and it will launch Fluent. And remember here, it will automatically detect if it is 2D or 3D. If you do it in the standalone Fluent version, you need to do it. Do not forget that. Always choose double precision. In my case, now I have 6 cores. I will put all of them and start. Okay, so we're going to launch Fluent in parallel, double precision, and it's a 3D case. Okay, we're inside Fluent. Okay, so here you have the geometry. Okay, so see that now we can rotate. Here we are in Fluent, previously it was fixed, so here you can access translate, zoom, rotate. Okay, and every different color that you see here will correspond to a different boundary condition. Okay, a different surface, now a different patch where we can assign boundary conditions. So remember, it's always a good idea, check the mesh quality, evaluate here. You see that now it's different from the 2D, so but still this is almost a perfect mesh. Info here, you can see how many cells you have. Okay, so let's set up this case. Okay, so and you go here, also it's important, check also the dimensions. Sometimes I have seen that it can give you problems. Okay, sometimes it will stick with the millimeters, or sometimes I don't know why it will take the inches. So always check here that you have the right dimension. So I see that this is my diameter and this is my length. So for me it's cool, it's okay. So first, general, for the moment we use pressure based, steady. Then we go towards viscous. Here we choose the default one. Okay, that is okay. Material, so air. So let me show you how to choose another material. So let's say that I want to use another in the library. So see here that you have Fluent database, and let me put here water liquid. You see that it will use the properties, copy, you add it, you close. So I will work with air, but just to show you how to add a new one. And here, let me choose this one, and this will be 0006. Okay, so this will give me a Reynolds of 100,000, close. So now we move to, so solid here, it will give you also default material, doesn't matter. This is only if you are doing conjugate heat transfer or fluid structure interaction, but here we don't have that, so doesn't matter what you put there. Fluid, cells, so operating conditions, and then you click here, edit. You can choose your material. So remember, you are new materials, you need to choose it here. So if you put water, you're going to use the water properties, but we're going to stick with air. Let me stay with air. Then boundary conditions. So inlet, velocity inlet, and I want to have normal magnitude, normal to the boundary. So put 1. Let me put here 1 and 1. So now I will use this setup here. Previously we used in the 2D this one, so we can put it as well, but let me put this one. You know, there are different combinations. Okay, so we know what it's doing, how to compute those values. So now outlet, this exactly the same. So okay, let me choose 1 1. Wall is a wall. We don't have symmetry here. Okay, that is for the 2D. Okay, and we're done. Here we don't need to do anything. Okay, the method, let's use this method. Okay, so let's check the memory consumption. So you can open your resources here. So right click here, task manager, performance. So now I'm using this memory. Okay, so let's see the memory overhead when we run using the couple. Okay, so let's use the default actions. Okay, default actions. Okay, monitors, residuals. Let's use the defaults. Report definitions. Let me add mass flow report. So inlet outlet. Give it a name. Mass flow. Just plot it. If you want to save it to a file, you can do it. Okay, we did it already. Okay, and let me add a new one that I want a surface facet average here for the Y plus. Okay, so turbulence. So compute the Y plus. So here Y plus average and plot. Okay, we have our two objects there. Report definition, initialize. Want to use uniform like this. See that it compute this quantity, so you can do your hand calculation. See, well, what correlations it use, or probably you have better values. Just put it there. It's up to you. Remember, always save every now and then those values. Okay, we're saving everything. So as you go back here to your Workbench, see here that in files, you have all the files that are being saved, okay? Okay, at this point, I think we did everything. Now we're ready to run. So let's put here 500 iterations. And off we go, calculate. And let's see the memory usage. Okay, which shouldn't be that much. But see that, okay, we have Y plus, okay, mass flow and scale residuals. Okay. So in this case, it wasn't too much, it's a small mesh, okay, but you see it was like 70, I think it was 80,000 cells multiplied by 3, so 300,000 gigs. No, 0.3 gigs of memory, sorry. Okay, so look at our work. Y plus is probably in the buffer layer, the area that we don't want to be. We try to avoid as much as possible. So if you want to fix this, you can go to the mesh, remesh, make your mesh coarser or finer. It's up to you. And here we have our residual. So let's wait a little bit. Let's see what happens. So mass flow also still oscillating. So see that this is not an absolute indication that you have converged. So always monitors another quantity. So see that in this case we're monitoring mass flow, but you can put also some monitors in velocity, pressure, whatever you want. Okay, so you see when you start to see that they start to stabilize, you can say that you have reached a statistically steady simulation. Okay. Okay, let's wait a little bit. Let's see what we have. Okay, we're back. Make a conversion about 150 iterations. You saw that it was a little bit slower. It's just 3D. Okay. The post-processing, you see that probably might be a good idea to iterate a little bit more. This, I leave it to you. You know how to do it. Change your monitors or you can turn it off. Okay, but you see that our Y plus is probably the really bad range value. So let's do now that we have a solution, we can do some post-processing. So the post-processing inside Fluent is not the best one, but you can do something. So later, the next tutorial will be to show you how to use another utility called CFD post, which is much friendlier. But let's do some post-processing here. So you go graphics, and we can plot, for instance, inlet and outlet. Let me plot velocity. So see that. Okay, wall, I want here. So your velocity profile there. Inlet, and then you have, where is my outlet? Okay, and here we have our outlet. So remember that the inlet is uniform, your outlet there. So also you can plot your pressure. Okay, so probably here it's better to put the pipe. You can see the pressure drop. So the thing is that how do we plot in the cut plane here? How do we generate a cut plane? So this is way to generate a cut plane. You go here, surfaces, right click, new, and use ISO surface. And I want to create in my domain, in the volume, I want to create an ISO surface of mesh, and I'm going to choose Y, I think, okay? Y coordinate. Compute, and it gives you the extreme. Now probably it's better this one, compute. Okay, no, let me choose X. Oh, yeah. Okay, so put here. So what you're doing here, you're creating a Y-plane, see the line here. So you can control it here, or you can insert directory value. Okay, so create with that name. And now you go back here. You have that plane there. And you can plot, for instance, velocity. Let me, voila. Okay. And you can do it exactly the same with lines. You have there many options. So see that you have your boundary layer, beautiful there. Okay. So let's do now again surfaces. So see that you have many options. Okay. So let me create a line, and so that was, I would put it in 6.9, almost in the exit. Okay, and this go, let's go from -1, 1, -1, no, this one should be 0, -1, 1. Okay, so see that I have this line there. Okay, here you can enable the graphical reference. So probably let me put it smaller. Soon there, bam, bam, bam. Okay, so it should be higher, so probably 0.2. Sorry, soon. Okay, let me put 0.5. So as you see, it's startable. Sometimes it's not the best post-processing here. So it doesn't matter. It doesn't need to fit perfectly the pipe, no, the extremes. Just cross, and then Fluent will do the sampling there. Create, you have your line there. And we can do the plot here. Reports, plots. So as we go here, XY plot, like within this 1D case, you select that line, and for instance, plotting, oops, I don't recall the, okay, velocity. So here again, you need to choose the right axis. So it's, okay, this was the one. So see the velocity profile. So you can compare with the 2D case. We should get something similar, okay? That is part of your homework, let's say. It's not a formal homework, just check that one, practice. And turbulence, again, see that turbulent kinetic energy. So see that, remember that the walls is 0. So you can do your normal post-processing as usual. You can write the files, everything. You can plot, for instance, also let me plot the velocity vectors. So let me plot that at the outlet. So see that, have there at the outlet. Or you can plot it in the cut plane, it's up to you. Let me turn off that annoying line, so go back here. And it's off. Okay, so you can choose different colors. As you see, you can do very complex post-processing here, but it's not very straightforward. I didn't talk about computing quantities after you have a solution. So see here that you have reports. So for instance, you can go fluxes, and here you can compute these fluxes. So you go here and you have it. So everything is conservative. You can go here, surface integrals, and you can compute, let's say, in the wall, you can compute the area of that wall, or you have many options here, okay? So if you want to do something else, so area weighted average, and let me choose turbulence, and let me choose the Y plus. Okay, so this is the area weighted average of Y plus on that surface. Okay, so it's up to you. You can do many scenes there. So you can do also volume integrals. So you can choose the domain, and let me choose the volume. So we know the dimensions. So it's up to you to see that the volume. So this is the volume of our domain. And forces as well you can compute. Okay, so forces are computed at the wall. So you choose here print, and you have in the reference axis. Okay, so see here that this force is 0. Okay, you don't have there. So this one also should be really low, and this one is will give you the force in this direction, and then from this force you can compute your friction coefficient. By the way, you can access that information as well. Friction coefficients, you go here, wall to the wall flux. This is what we call skin friction coefficient. Okay, and you have your skin friction coefficient. It is computed, it is normalized using the here reference values. Okay, so you need to input here the reference values to normalize that. It will be the same with the forces, with the coefficients. You compute coefficients here, there are coefficients. This will normalize using these quantities. Okay, so you should do this manually. Okay, Fluent doesn't know that. Okay, okay, so I think that is all in this case. So you can do the same setup with the other mesh. Okay, exactly the same. Also, you can play around, change your Reynolds number, see what happens. So you have many cases in Fluent. Later I will show you that when we do this live. And we have many options there, many things to do. So in the next video, let's move and do the post-processing using CFD post. So see you later.